Welcome or welcome back to Why This Universe. So last time on our show, we talked about the central equation of quantum mechanics, what's called the Schrödinger equation. And in that episode, we talked about two things that make this equation unique in a mathematical sense compared to all the other equations in physics. One of these features is the fact that the equation is linear. What that means is that if you have one possibility that's allowed by the equation and another one, two things that might happen, then you can add them together mathematically and get a third possibility. So for example, if you have a particle that can be in one location or it can be in another location, you have a third possibility that it's in both locations at once. And this gives rise to superposition and a whole host of odd behaviors that are typical of quantum mechanics. Now, this is a pretty essential part of the theory of quantum mechanics. However, you could try taking the Schrödinger equation and then adding a piece that breaks this rule, adding a term that's nonlinear. Physicists do this sort of thing all the time. They like to play with the math and see what happens and then see if what they get is possible in our real world and match it to experiments and yada yada. But it turns out that when you make this particular change to the Schrödinger equation, you get very bizarre results, like something out of a ghost story level of strange. And while most people think the Schrödinger equation is probably fully linear, there are some physicists who are still exploring the possibility that it has this extra nonlinear term. And our guest today is one of these physicists, so let's see what he has to say. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. So we have with us today, again, David E. Kaplan, who's a theoretical particle physicist and cosmologist at Johns Hopkins. His work focuses on things in particle physics and cosmology having to do with physics beyond the standard model, especially in connection to the Higgs boson, supersymmetry, extra dimensions, dark matter, all that sort of fun stuff. Recently, however, and I mean since, 2021, 2020, something like that or so, he's been working on something that I and probably most physicists would consider to be much weirder than any of those things. And if any of this turns out to be true, it would totally overturn everything we think we know about quantum mechanics. So we thought we'd have him back into on the podcast to talk about what we call nonlinear quantum mechanics and just how much this would be a radical departure from everything we think we know about the quantum world. Thanks for coming on, David.
Oh, my pleasure. Good to see you, Dan.
So let's just start by talking about standard linear quantum mechanics.
Yeah.
We've talked about quantum mechanics a lot in the show. We did a recent episode on the Schrödinger equation. So our audience will know a little bit about it, but in a 2-minute elevator pitch, what is quantum mechanics? Yeah, no pressure.
Fantastic. Oh my gosh. Well, we thought of the world as being made of billiard balls with forces in between them. And something happened with quantum mechanics. It was discovered in a totally bizarre way, but it describes the fundamental laws in a completely different way than this billiard ball Newton's forces does. It's completely different. One way to see that it's completely different than normal billiard ball physics is you take an atom, like the hydrogen atom, it's just made of a proton and an electron. And the structure of that atom is such that the electron has no, we'll call it angular momentum. The lowest energy state of the hydrogen atom is in effect perfectly spherical. This means that any notion of an electron traveling around a proton the way planets traveling around the sun look is completely wrong, even though we were taught that in school. So then you have to ask what exactly is happening there. And it turns out that the electron is not well described as a particle in that context. It's well described by effectively a wave. And you could imagine a wave, say, if you had a bowl of water and you drop a pebble in it, the surface of the water would oscillate up and down. In physical space, you see a wave oscillating up and down. It's spread out over the entire bowl. You wouldn't describe it as being in one location or another. It's that entire wave acting on the surface of the water. An electron is also a wave, but in an interior, let's call it mathematical space, because we don't know how else to talk about it. But there's an internal wave structure associated with the electron. And the electron is literally spread around a globe with the proton at the center.
And yet, if you measure an electron, you find it at one place.
We'll get to that. So people often say things like, when they talk about quantum mechanics, particle, wave, nature, da, 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 da. So I'll tell you how I think about it. I think of the electron as just a wave. That's all it is. Now, you can ask what happens if you try to interact with that wave. And there's a rule in quantum theories that have been so far preserved, which is that all interactions are local. And so when you interact with the electron wave with something else, let's say you send in a high energy particle of light or a high energy electron, different electron, you can, at higher and higher energy, determine to a better and better extent where that interaction occurred in that wave. And because of that, because the interaction is so local, we call it a particle. We interact at a point and it's a particle. So we've talked about particles for so long that when we got to quantum mechanics, we still talk about particles. My field of study is theoretical particle physics. I do not think there are particles. I think there are quantum states that behave the way particles behave, and that interactions can be made to happen at a smaller and smaller length scale, which then appears point-like.
It's fun. I can't help but notice that you, even in your example, you said you send in a particle of light to interact with the electron wave, but I assume you also mean that that particle of light is a wave.
Absolutely.
Okay, so let's talk about the Schrödinger equation in this context. So in standard quantum mechanics, very slow-moving particles follow this equation. Schrödinger came up with in 1924. And this equation is, importantly for the purposes of this discussion, linear. It includes linear evolution with time. Explain what linearity means in this context to a physicist and what its implications are for quantum mechanics.
Sure. Anytime you have a law, a rule, which is linear, and what a law or a rule is it's an equation. So you have your equation, that's the law, and then you have your situation. I throw a ball, into a hole, or I roll down a hill, or whatever I do, and then that situation gets plugged into the equation, and the equation tells you what happens. It gives you the time evolution of your system. If that equation is linear, then you can have one solution to the equation, and you can have a second solution to the equation, and then a third solution is adding the first and second solution, which means that every solution is true, and every combination of every solution is also true. This is super important in quantum mechanics. First of all, quantum mechanics is the only, if it's complete theory that is linear. There is no other theory in nature which is linear. It would be too boring. Nothing would happen, essentially. But somehow quantum mechanics is crazy, and therefore even a linear theory does crazy things. So let me tell you what that means for quantum mechanics in a very simple way that might make you nauseous. So you are sitting wherever you are, and that state of affairs, you sitting there calmly and not moving or anything, that is a solution to the Schrödinger equation. You could describe all the atoms and molecules in your body and everything, and you could ask, how do they all evolve? They evolve with the Schrödinger equation. On average, it looks like Newton's laws, but deep down, it's really the Schrödinger equation that tells you what happens. That's a solution to the Schrödinger equation if you're sitting in place A. If you're sitting in place B, somewhere else, That's also, of course, a solution of the Schrodinger equation. You could be sitting anywhere, and these are all good solutions to Schrodinger equation. That means there's another solution, and the other solution is the sum of you sitting in location A and you sitting in location B. That also solves the Schrodinger equation, which means you're allowed to have quantum states which are combinations of you sitting in macroscopically different locations. You, yourself.
What we call a superposition.
And a superposition is a sum of two solutions. That's exactly right. So this is the thing that freaked out Schrodinger, because Schrodinger realized that what his equation predicted was that you could have a little quantum effect, which is that there's an atom and it decays, and it has some probability of decaying at various times. And if it, let's say, decayed before a certain time, then it could trigger a poison gas that would kill a cat living in a box. And if it decayed after a certain time, then it wouldn't generate that poison and the cat would stay alive. Which means that you could experimentally, in principle, create a quantum state which was a combination of the cat being alive and the cat being dead at the same time, whatever that means. That is a consequence of the Schrodinger equation. And so now you ask, okay, well, that's ridiculous, or it doesn't make, this is a logical fallacy. There can't be that. We've never seen a quantum state with the cat alive and dead at the same time. We've never seen a quantum state with me sitting here and me sitting over there at the same time. So something's wrong, obviously wrong. And that's why people invent interpretations of quantum mechanics. They say, yes, the equations say that, but if somebody measures something, it hocus pocus collapses and part of that state goes away and nothing happens. There is no mathematical structure for which that is true. We have no theory of quantum mechanics where hocus pocus happens and you remove things. You just do it by hand when you teach in a class because you don't want to really teach the reality of what quantum mechanics predicts, which is that there are quantum states where the cat is alive in one part of the state and dead in the other part of the state. If the cat is dead and I walk over and open the box, I react. My reaction, all of that, me as a pile of atoms, comes from the Schrodinger equation. It is time evolution of a system where there's a dead cat. I'm walking over, I open the box, I see a dead cat, I respond. My brain responds, and however it does, I do some bury the cat, funeral, whatever. I do something. There's a time evolution in that system. If I open the box and the cat is alive, it has its own time evolution. I say, oh, there's the cat. I pick up the cat. I feed the cat. So, and something is happening in my brain. Okay, those two time evolutions can also be added together. So if the cat now is in a situation where it is both alive and dead, that's the combination. That's the quantum state of the universe. Me walking over and seeing the cat, I know in a linear theory that I can add the solution to the equation where I open the box, the cat's dead, I react, to I open the box, the cat is alive, I react. I'm reacting in the live cat, I'm reacting in the dead cat, I don't see both. I'm part of that quantum state. I'm in a combination, which means the theory does not predict that I would see those states. It only predicts the existence of those states.
So good. So we've got this linear theory that allows for things like superposition between different states. Now, tell us how you might break this linearity. What it might look like if some sort of quantum mechanics was not linear, as you've been contemplating with your collaborators recently.
Right. Yeah, this is with Surjit Rajendran. Beginning of COVID, we were sitting around. To be honest, what really happened was, for many, many, many years, there were all these experimentalists, say atomic and molecular AMO experimentalists, doing beautiful experiments, testing all kinds of things, measuring all kinds of things using quantum states of atoms and molecules. And they wanted to test quantum mechanics too, because they have these very sensitive, delicate experiments. So they go out, they look for people who modified quantum mechanics, crackpot sort of things, make no sense, but they want to because they really know they're testing quantum mechanics. And then Surjit or Savas Dimopoulos, who's my postdoc advisor, or I, or various people say that theory doesn't actually make any sense. But there was a desperate desire to test quantum mechanics, and to test a theory, you have to know how it could be broken. So you'd need, let's call it a test case scenario where you had a complete, well-defined theory, but did not follow the rules of the original theory of quantum mechanics. And so what could you do in this theory? And the simplest thing to break was adding nonlinear terms to the Schrodinger equation. Terms that depended on higher powers of the wave function, of the state of the universe. And that is a very important change. And it's very important because, as I described to you, quantum mechanics is sort of crazy. It predicts the existence of these superpositions of things that don't sound like we could have those in the world, a live cat and a dead cat, or people being in completely different locations, quote, at the same time. When you modify the theory a little bit, you kind of open Pandora's box. You become sensitive to the fact that those crazy quantum states could exist. Now, we're not the first people to think about making quantum mechanics nonlinear. Actually, in 1960, I think one of the founders of quantum mechanics, de Broglie, wrote a whole treatise, a whole book on modifications of the Schrodinger equation, adding nonlinear terms, saying that quantum mechanics is the only linear theory in the world, therefore it's probably an approximation. And unfortunately, he spent the time just solving complicated differential equations and not thinking about the physical consequences. In the late 70s, there was a set of thoughts that people thought maybe the whole world is quantum, but gravity is classical, meaning gravity doesn't follow quantum mechanics. And that's because people were confused about how to make gravity quantum. It still are. And Kibble, a great physicist in the UK, Tom Kibble, showed that if you do that, then the Schrodinger equation becomes nonlinear, and you lose this superposition principle of quantum mechanics. And he even said at the time that there shouldn't be anything wrong with it. And he solved very simple examples. But again, didn't dive into the physical consequences. It was not until Steven Weinberg in 1989 wrote down the Schrodinger equation, explicitly added nonlinear terms, and then tried to think about tests of it. That he did something with a lot of formalism, and the tests he thought of were, in a sense, incredibly simple or even simplistic. But because it was Steven Weinberg, there were 27 papers after that where people were trying to test Steven Weinberg's theory. Steven Weinberg, discoverer of the standard model of particle physics, Nobel Prize, 1979, I think. It 6 months later was shown to be a theory that violated relativity. It was shown by a young professor named Joe Polchinski. In a few pages, he showed that Weinberg's theory, in a sense, didn't make sense. Information could travel faster than light. But in that same paper, he said you could then modify the theory if you followed a certain set of rules that would make it not violate relativity. And then he said a few things about it and then moved on to other physics.
I want to emphasize how big a problem it would be to violate relativity in the way we're talking about here. This is the sort of thing, if you can go faster than the speed of light, then in some frame of reference, you can go backwards in time. And if you can go backwards in time, you can, famously kill your grandfather before he meets your grandmother, and then you never get born and you never go back in time, and then paradoxes ensue. So the whole causal structure of the universe falls apart if you do this sort of thing, right?
That's right. I mean, you have to decide how you're going to break it, but yes,
right.
The core elements of what we know so far break down in a serious way. And so you can't just break it and then not pay attention to it. You have to find that there's a theory well defined. And so naively
break it gently.
break it gently, or break it in a specific controlled way. Yeah. I like to break things, so I don't want to dismiss all breakings. But yes, immediately he said that, and immediately Weinberg said, "Oh yeah, that was a mistake," and they moved on from that. Sergeit had this thought: you could take Weinberg's theory and you could add a term to make sure that the communication of the quantum state with itself only traveled at the speed of light or slower. And so he added some term. It was an ugly term, but it worked. And we're like, oh, holy cow, okay. And we started working through it. And since the theory of the world is not just quantum mechanics, it's so-called quantum field theory, that the world is made of fields, we needed to put it into quantum field theory. And so that took some time, but we discovered once we put it into quantum field theory, actually the theory was infinitely simpler than what we had to start with, than Weinberg's version. It actually more closely matches what Kibble wrote down in 1978. And so we took that to mean that we had a very clean, self-consistent modification of quantum mechanics where superposition breaks down, and we should figure out how you test it. And we discovered many things. For complicated reasons, all of the tests of Weinberg's version of the theory were completely irrelevant. It had to do with the fact that this term appearing in quantum field theory spread out the effect over the volume, over the wave of the state that you're looking at. And that was not something that Weinberg paid attention to, because only when you realize you have to do it in quantum field theory do you end up discovering that it depends on the size of the wave function, gets suppressed by the size of the wave. So we invented a whole series of other tests. But I'll say what the core insanity of this theory is, which is that, as I said, you could have these quantum states where you see a dead cat, you see a live cat. And while this quantum state is crazy and is predicted by the equations of quantum mechanics, Schrödinger's equation, we never see it. We never experience that. We are split up. There's a version of us where we see a live cat, a version of us where we see a dead cat. Every single version of us only sees one thing. If you add this nonlinear term, that nonlinear term now depends on the entire quantum state of the system, which means there's an effect which is sourced by both worlds. The cat's alive, the cat's dead. So in principle, if you do an experiment and you can create a source that is detectable in your world in one location, and in the other version of you, other world, in another location, then a nonlinear term means you can see both. You can see an average of both worlds.
You can see parts of the superposition that normal under linear quantum mechanics you can't see.
That's right. You can see the versions of reality which exist in the quantum state, but not in your direct interaction experience. There's now something in the background which depends on all parts of the quantum state, even things that you weren't directly involved in. It's insane. I don't know how else to say it.
This is something I've seen in a lot of like fairly bad science fiction where they try to talk about quantum mechanics where you can kind of jump across branches of the wave function or something. It's almost like that, right?
Yeah. There was one, we worked on this, and right as before we were finishing, or around the time we were finishing, there was a great series on TV. I can't remember what it's called, but J.K. Simmons was the star of it. But it was one of these things that during just after World War II, the beginning of the Cold War, there was some East German scientist that made a connection between the split worlds in quantum mechanics, and then they interacted with each other, and then because they split, they did different things, and then there was a lot of drama.
Are you talking about Man in the High Castle? No,
that's
but that's a solid example of the kind
alternate
of
history.
Like,
that's right.
Yeah, well, and using quantum mechanics too, and maybe they're using nonlinear quantum mechanics from the way it was depicted.
That's right.
Okay, wait. So This might be like a crazy, naive, nonsensical question, but you're saying that you can see something from the superposition, like from these alternate realities in some sense.
Yes.
What is it that you're seeing?
So here's an example of an experiment you could do. Let's say you have an electron. An electron is a special particle in that it has an internal spin to it. It's like even a tiny magnet. But because of the super weird quantum nature of the electron, when you measure the magnetic field along a specific direction, or the spin, you can only get two values. It's either spin pointing up, or the magnet pointing up, or the electron spin pointing down. And the way you measure it is you send an electron through a big magnet, and it either pulls it up or it pulls it down. So this was a famous experiment done, the Stern-Gerlach experiment in the early 20s, with this shocking result. You send an electron beam in, and you think it would just get spread all over the place, and instead you get two spots. So this quantum nature of the electron, you say, well, I could prepare the electron spinning up, or I could prepare the electron spinning down, but I could also prepare the electron spinning in some other random direction. When you do that and you send the electron in, you'll discover there's a probability that you see the electron go up or see the electron go down. If you send in 1,000,000 electrons, you'll maybe see, and they're all prepared in the same state, maybe you see 60% of them go up and 40% go down. That 60-40 split actually tells you something about the original quantum state that you prepared them in, that it's pointing slightly up along a different axis. But you see there's a probability there. But the Schrödinger equation tells you exactly what happens when you start from a certain quantum state and you get to another quantum state. So what's actually happening in the quantum theory, in linear quantum mechanics, please don't blame me, there's no interpretation here. What's actually happening is the spin goes in, the quantum state of the electron is now split between an electron going up with its spin pointing up and an electron going down with the spin pointing down. It hits a screen. Now the quantum state of the system is a screen with a little light, something turning bright on one side, photographic plate, and something turning bright on the other side. And then I walk into the room, I take a look at the screen. Now the quantum state is me seeing the upper dot or me seeing the lower dot, a sum of those two. Light goes into my eye, my optical nerve, my brain reacts. Each part of that quantum state is evolving. So that means I can create from a little tiny particle a macroscopic superposition. We call them Schrödinger cat states, where I am, seeing this thing or I see that thing. Now, let's say I do such an experiment, and if the electron went to the upper dot, it turns on a laser pointing to the left side of the room. And if it goes to the lower point, it turns on a laser shining on the right side of the room. Now I go in, I see where the dot is, I see the laser shining. If quantum mechanics is nonlinear, meaning there is a full effect from the full quantum state acting on me and everything else, even in a very tiny, weak way, I walk into the room, I see the laser pointing a specific direction, there will be a tiny spot of light in the other direction, even though there is no laser in my part of the world pointing in that direction. I will see the effect of the other world, the other part of the wave function on average, and it will contribute to a tiny spot on the other side of the wall.
Things can leak across the different parts of the wave function.
They leak. When we were first writing this paper, so my mom, as of course, Kismet would have it, she is not a scientist. She believes in all new age properties of everything, quantum healing, energy healing, different, past lives, out of body experience. She's like all the way in all alternatives, all possible things, right? She's seen her dead father. It's so many things that she's just joyous about it and she's hilarious about it, but she truly believes her shelves are full of books that all contradict each other. It's fantastic. So I realized that this is an actual scientific theory where you could predict the existence of what you might think of as ghosts. That the other part of the world leaks into ours, and there are coherent effects from the other part of the world that can cause things to happen in our part of the world. And if you could set up just things just right, it's just the other part of the wave function that we're interacting with, and we don't have direct explanation for what that background weirdness is.
All right, so you construct a Schrodinger's cat experiment. You open the door, and you're saddened to learn the cat's dead.
Right.
But it's not completely dead. There's this lingering quantum alive cat out there, just a little bit in your world of experience.
Yes,
still?
in principle, that live cat can have some, if it can emit some coherent waves of some kind, if certain properties of the cat, yes, you could potentially have effects from the certain properties of that cat, if it's that discrete, really.
And more broadly, more generally, like every quantum possibility that ever could have played out from the initial conditions of the universe, all of that is just gently manifest in our universe now.
That's right.
Okay.
It's very, yeah. So it's very reasonable to think that our ability to do something with this effect is very weak. That the universe has split so many times that even our realization that quantum mechanics could be nonlinear could only be happening in an extremely tiny part of the wave function of the universe. So
Sure.
whatever I do, I cannot affect the broad wave function of the universe. I can only affect this tiny, tiny fraction of it. And the effects from that would be similarly extraordinarily tiny. That is certainly a possibility, and even a reasonable possibility. But if the effects are not too small, and we discover it, you completely change the world in an insane way. And this is because if quantum mechanics as written in the normal way is right, you can do that. You can measure the spin of a particle. Is it up or down? And then you say, okay, I measure up or I measure down. If I measure up, I have a hard calculation I have to do on a computer, which I can split into two. On my laptop, I'll do one half of the calculation. But if it's spin down, I'll do the other half of the calculation. And what's happening in quantum mechanics is both halves of the calculation are being done at the same time in different parts of the wave function. Great. You've parallelized the job, but in linear quantum mechanics, I'll never see the other cat, so I'll never see the result of the other half of the calculation. But if there's nonlinear quantum mechanics, one of me could send signals to the other one of me with the result of that calculation. I have now parallelized, using the quantum worlds, a human activity. And if I measure 2 spins, there are 4 possibilities, 2 squared. If I measure 10 spins, there are 2 to the 10 possibilities. And so I can parallelize an exponential number of worlds, and then if they can all signal to each other the results of those calculations, you don't need a quantum computer. You can simply parallelize all human activity. Not just making a computation, but you want to look for sources of water in the desert. You send out probes. You do it in 2 to the 10 worlds, which is a very large number of worlds, and you get back data and you immediately learn things.
Anytime you want to do something that has different ways you could do it, you can just do all of them.
That's right.
That's the idea. Yeah.
Simultaneously. And the only new thing is that those worlds can communicate to each other.
Yeah.
So that most of that craziness, I would say, lives in quantum mechanics. It's only when you turn on this little extra term, you have access to it.
Yeah. It all happens normally in normal quantum mechanics.
Yes.
But you lose your connection to it.
Yeah.
Because of the linearity. Okay, good.
And we're part of the system. So we can't help ourselves but we call it entangled. We get entangled with the results of an experiment.
Right. All right. So just to make completely clear for our audience, there's no evidence of any of this, right? This is a possibility.
0.
Yes. What are people doing to try to obtain evidence or rule out the sorts of nonlinearities we're talking about here?
There are so far there's a couple of ways that nonlinearities could appear. And we like the versions where it's coupled to forces of nature. And so very simple versions of the theory, like I said, if light itself has a nonlinear term, then you could see lasers pointing from other worlds. You could see a little bleed from that. If those terms live in gravity, then you could get gravitational sources from the other worlds. You could see gravitational pull from other things. So the naive thing to do is to set up experiments where you split the world, you have both things happening, and look for effects where one affects the other. There were experiments done at Berkeley now to test our theory, which used very beautiful, they're called ion traps, which is a charged particle trapped into a little space using electromagnetic forces and putting that charged particle in different quantum states. And you could test to see if the quantum states interfere with each other. You can do crazier things too, which is similar to you measure a spin, which way it's pointing. If it's pointing up, you turn on a large voltage in in some capacitor. And if the spin is down, you turn off the voltage. But then you measure the voltage. Every time it turns off, you measure to see if there's any residual voltage. So these experiments have been done, and they put constraints on the electromagnetic parameter of roughly, it's just a number. So 1 would be full strength, and that number is roughly 10 to the minus 15 or less. So it has to be very small.
So like 1 would mean it's completely nonlinear quantum mechanics.
That's
in
right.
this respect.
That's
okay,
right.
So there's 10 to the minus 15, so 1 in a quadrillion piece of nonlinearity
That's
is still
right.
allowed.
That's right. And you could say, oh, well, it's so small, then it's probably not there. Yes, possibly, reasonably. But because of the dilution from the early universe, because we're not necessarily the whole wave function, we expect that number to be small. We just don't know how small it should be. Because that number not only incorporates the fact that maybe there's a nonlinear term, but it incorporates how much we can influence the quantum state to see that nonlinear physics. So in that sense, we're testing it if we can see it in local experiments. We have also realized that nonlinearities, even if we can't control them, can affect the background physics of the universe. It can affect the gravitational field in the universe. It could affect the Higgs field. We have a paper coming out where we've realized that if you have a nonlinear term in what's called the Higgs potential, that you can easily solve the hierarchy problem which is something that people have been trying to do for decades. And it's almost a trivial fix if nonlinear quantum mechanics is true. So we are seeing ways that either you could detect it, or even if you can't detect it, it has a very dramatic influence on what the actual theory of nature could be, and maybe could explain some problems.
Fascinating. Okay, so I, for one, David, am cheering for this being manifest in nature. I've always wanted to live a life of a physicist while something truly profound was moving under our feet that nobody understood, and you have to finally figure out, in real time how to think about this stuff. I wish I'd been there in 1905 for Einstein's miracle year. I wish I'd been there in 1924 for Schrödinger equation and de Broglie and these guys, maybe, just maybe, we could be witnessing. Well, I mean, there's no evidence for it, but I hope there materializes evidence for it one day, so we get to do that all together. Sounds fascinating.
I do too, all crazy ideas are totally crackpot until one actually gets discovered. And
Sure.
I would say a great example of that is Planck and Einstein. When Einstein decided he loved Planck's idea of quantizing something, and he said that the electromagnetic field itself is quantized and made of quanta, photons, which he didn't name, and he didn't even call it a particle. But when he said that, it was completely insane, because the theory of electromagnetism was the highest ideal of any physical theory. Maxwell's equations, how electricity works, the relationship between electricity and magnetism, electromagnetic waves being light and traveling the speed of light. That was just a complete revolution in what looked like a complete understanding of how the physical laws work. And so for Einstein to say that, no, it's not an electric field, it's made of quantum lumps, seemed completely insane at the time. Of course, it all bore out. And by the time everybody agreed that that was true, Einstein was very suspicious of quantum mechanics, although he knew it was the best description we had so far.
Why This Universe is produced and edited by me, Shalma Wegsman, and my co-host is Dan Hooper, a physicist at the University of Wisconsin-Madison and the director of the Wisconsin Ice Cube Particle Astrophysics Center. If you want to support us, consider subscribing to our Patreon for as little as $3 a month. And in return for your support, you get ad-free episodes and the ability to ask us questions directly for Ask Us Anything segments. You can find that on patreon.com/whythisuniverse. Thanks for listening.